One way to describe the change of energy in a reaction is through an energy diagram. Now we must consider when we have a reaction, why are they occurring? And a collision theory says that there's two things that when a collision occurs that has to occur for a reaction to result. So I might say there's three things, because the first thing for a reaction to result, we need a collision. So we want the molecules to come into contact with each other. So then the second thing we would need is enough energy. Now, so what happens, remember from our previous discussion, in order for a reaction to occur, bonds need to break. And the breaking of bonds is an endothermic process requiring heat. So, our energy. So, bonds need energy to break. And so we have to have enough energy. If there's not enough energy, then even though two molecules might collide, if there's not enough energy, the bonds won't break and the reaction won't occur. We call this the minimum amount of energy. This is called the activation energy. I always imagine like when you activate something, you get it to work or turn it on. And so the activation energy is what you need to get a reaction to get turned on or to work. So we need activation energy. The abbreviation for activation energy is E with a lowercase a. The other thing you'd need after a collision is something called a favorable orientation. Well, this is because molecules, are three-dimensional, and sometimes when they collide at each other, the two atoms that are going to need to form a new bond may actually be very far away from each other. That would be an unfavorable orientation because the two atoms are separated between space, and also there might be other atoms in between them. A favorable orientation would occur when two atoms maybe hit head-on that we're trying to get to react. I can try to draw an illustration of this. So let's say the pink one needs to react. We have a pink and a peach, salmon kind of color. Okay, there's molecule A. And we want molecule A to react, and molecule A is going to react with molecule B. And there's a green molecule, a green atom, and a blue one. And this is molecule B. Now let's say we're going to react molecule A with molecule B, and what we want, our new substance, is going to have the pink one with the blue one. So you can see if these two collided head-on, even if they had enough energy, then the pink and the blue are separated by distance, and then we also have these two atoms in between. That would be unfavorable. Again, assuming I'm making up a fake reaction where the pink and the blue are what I want to form the new substance. But let's say, for example, instead of the pink, the molecule A, instead of being oriented with the pink farther away, it had flipped around, and now the pink was right there. And then the other molecule with the green, molecule B, had also flipped around. Oops, sorry. Then, now when they collide, and these two are the new ones that I want to get together, this would be favorable. Favorable. So now my new molecule, just saying that this is what I wanted to form, C, these two would be right next to each other. And so the bond could break, and then they would form because they would be right next to each other. So when we talk about orientation, it simply means are the atoms that need to get together to form our new compound, are they in a orientation or a location that is favorable to them getting together. Now we are going to write energy diagrams, and I have an example of endothermic and exothermic. Now we're not really drawing diagrams for specific reactions. Rather, we're trying to understand in general what these diagrams can tell us. You can see down here I do use EA for the activation energy, which is over here. That's the amount of energy we need for the reaction to proceed. Now what I would like to do on the next slide is redraw these diagrams, kind of talking you through how I think about them. So I'm going to draw them side by side. And on this side, on this side I'm going to draw endothermic. And on this side, I'm going to draw exothermic. These, again, are energy diagrams. So they are just kind of mapping the energy as it changes throughout the reaction. And we're doing these for generic reactions, generic endothermic and exothermic. Now, what they would both have in common are these axes. And on the y-axis, this is energy, and as you go up the axis, it's increasing. And on the x-axis, this is time, or the progression of the reaction. So we're going from beginning to end. It's sometimes labeled progress of reaction or time. It's just from when the reaction starts to when it finishes. Now, remember, all chemicals have potential energy inside their bonds, so our first line is never going to be at 0. And in an endothermic line, I'm just going to draw, this is a line I'm drawing, and I'm going to label underneath what it's representing. This represents the reactant energy. Now, if this is an endothermic reaction, we know that we're going to put heat in, and so leaving a space, because we go on a trip, in quotes, we're going to go from one place to the other, but leaving a space between, I know that in an endothermic, we're going to put the products higher than where we started because, by the definition, heat is absorbed during the reaction overall. So I know that I end up higher than when I started. Now, in exothermic, the definition is that heat is released. So if I think it through again, I'm going to start my reactants, and really where I start doesn't matter, but that line represents my energy of my reactants. And then I know heat is released, so when I release something, I lower, and so the products, leave a space there, but the products have to be somewhere lower than your reactants. And again, it really doesn't matter as long as their products are lower than your reactants in an exothermic reaction. So in the endothermic reaction, coming back, so we start at our reactants. Now what happens? We need energy to break a bond. So what we see is the energy goes up as we have to have energy absorbed to break the bonds. Once the bonds are broken, new bonds are formed and energy is released, and we go down. Right? So we're going up when the bonds are broken, and down, energy is released when the bonds are formed. And on the exothermic, it does the same thing. We go up when the bonds are broken. Once the bonds are broken and the new bonds are formed, energy is released, and we go down. So we get something that I call like a mountain. It's going on a trip. It's going over this mountain. Now, if I could draw an imaginary line, and I'll just draw it in blue dots for where my reactants are on both reactions. This isn't part of the energy diagram, but it helps me visualize what's going on. So labeling this, the activation energy, or the amount of energy it takes for this reaction to occur, is the energy from where I start at the reactants all the way up to the top of the peak. That's the minimum amount of energy, my activation energy. And on the exothermic, it would be a similar thing. It's from where I start on the reactants down here, all the way up to the top of the peak here. And the peaks do tell us information. The taller the peak, the more activation energy is required. And we'll see that also gives us a window into how fast the reaction will occur. So the activation energy is from where the energy of the reactants are all the way up to the top of the peak. Now, another thing we have is something called a transition state, and I'll just put a little asterisk up here. A transition is when you're in between something. And in this case, your transition state is when you're in between the products and the reactants. So if I can imagine a place where all the bonds are broken up here at the top of my peak, but at the same time, it's although the bonds are broken, the new ones haven't been formed, so it's in transition. As soon as the new bonds are formed, then we release energy and go down in energy to the products. The transition state would be at the same place on the exothermic. It's at the top of the peak. And again, remember, the energy goes up as the bonds are broken. And once the bonds are broken and the new ones are formed, then it goes back down. So up at the top of the peak, we have this transition state. And then a final place is called the heat of the reaction, or our delta H. And delta H tells us the difference between the reactants and the products. Now, delta means change. So if I was going to write delta H as a general form, delta H always equals the energy of the final one, which is the products, minus the energy of the reactants. So if I look here and I say the energy of the products minus the energy of the reactants, if you're looking very carefully at this, products are higher than the reactants. So if you take a larger number and subtract a smaller number, then you get a positive value. Remember, one of the things we said in an earlier video is that endothermic reactions have a positive value for delta H. That's because the products have higher energy than the reactants. Now let's take a look at this delta H. So this would equal the energy of the products minus the energy of the reactants. Well, here the products are lower in energy than the reactants. So you're taking a lower number and subtracting a higher number. And when we do that, we get a negative value. So for an exothermic reaction, delta H has a negative value because the products are lower in energy than the reactants. So see, in the first video, I just told you that, but now you can start to visualize and understand why. So for me, these energy diagrams kind of help me visually remember some of the things that we learned initially about energy and reactions. Now, another thing that the activation energy does is help us understand how fast a reaction is going to go. And you can see here that if you have the higher your activation energy is, the slower your reaction. In my mind, I kind of think of it like the mountain, right? A higher activation energy has a higher mountain to climb. It's that over the top part. So the higher that mountain is, the slower the reaction will go. Now, there are some ways that chemists can try to change the rate of a reaction, and here are three. We can increase the concentration, because increasing the concentration increases collisions. And increasing collisions will then increase the chance that those two things will get together and have a reaction. So you can try to increase the reactant concentration and see if that will make the reaction go faster. Another thing we can do is increase temperature. Increasing the temperature adds energy. We know that another thing that we need when we have a reaction is that activation energy, that EA. So the more energy I have, the more molecules can get over that mountain or go over the activation energy, and the more reactions I can have. So usually when you increase temperature, you increase the reaction rate. You know, our body does this naturally when we're fighting, when we're sick and we're trying to fight our sickness, right? What do? Oftentimes our body gets a fever. And fever is one way that the body adds heat to the system in order to help the reactions go a little bit faster. But we know as humans we can't handle too much extra heat. The extra heat also stresses our cardiovascular system. So we can't just keep cranking up the heat on our bodies like we might in a reaction. But in general, that's what increasing the temperature does. It adds energy and can help our reactions go a little bit faster. And then finally, there's something that's called a catalyst. Now you can see here what a catalyst does, and I'm going to draw a picture of it. It lowers the activation energy. A catalyst is a helper. It's not a reactant or a product. It does not get used up in the reaction. And so it helps the reaction by finding an alternate way for the reaction to occur. In essence, what it does is lower the activation energy. So let's draw an energy diagram, and it wouldn't matter if I did endothermic or exothermic. Catalysts would have a similar effect on the activation energy. So I'll draw an endothermic reaction like this. So remember, these are my reactants here. These are my products here. This peak from where my reactants, I can kind of draw a little line here to kind of see, from where my reactants start to the top of the peak is called my activation energy. Now if I added a catalyst, what the catalyst does is tunnels through this. It finds an alternate path, and so my activation energy lowers. So if a catalyst finds an alternate path for the reaction and in essence lowers the activation energy, which results in a faster reaction. So we still have a diagram, but the peak, activation energy, the mountain would be smaller because the catalyst I was thinking like going through a mountain with a tunnel. It finds an alternate path that results in lower energy use, and so it is a faster reaction.